Okay, so during the lectorial we did a proof of Pythagoras using my favorite approach, which is the box inside a box. You have a box and then you tilt the other box inside, and that one's relatively straightforward. Have a chat about Einstein's proof that he did when he was a boy. So Einstein didn't like maths that much when he was a boy. That's a joke. Don't know if he did or not, but he didn't like the fact that so many Pythagoras' theorems were done using maths when you could use geometry. So this is Einstein's proof, roughly speaking. So first of all, let's draw ourselves a triangle, and we're going to say I'll give this A, B and C. Mine's looking a bit 45 degrees, but let's say it's not. So here we have an angle alpha, and here we have an angle beta. So the first thing is that Einstein said, well, what happens if you draw a line that's perpendicular to the hypotenuse, so that it then cuts through that point there? In that case, you've created two right-angled triangles there. So you've now got an alpha there. So use complementary theory here for finding your angles. So if that's alpha, then this must be beta. And if this is beta up here, that must be alpha down there. Okay. So I've now got these two triangles which will obviously have the same area as this triangle here. Next thing is to say, well, could be a few things here, but next thing is say, let's point out that you could point that out by saying you can flip these if you wanted to. So we would flip them down the edges here. So your beta's there, your alpha's there, and your beta's there, the right angles are here, and your alpha's here. So I've flipped out those smaller triangles, and I've still got my original one here. And that's my right angle there, and that's alpha, and that's beta here. So what do we say now? We can go back to, do we know what the area of a triangle is? Well, you can sort of imagine this triangle and sort of say, yeah, I can measure that triangle. I can flip that around, and I'll put the C on the bottom, yeah, and then I will then put it up like that, So I've got the C on the bottom there, the right angle at the top there. Now I've sort of switched it so the beta's here and the alpha is here. Okay, so the area of the triangle depends upon the base times the height divided by 2. The height I don't know. Well, unless I'm using some little trick or something like that. But the height I'll call height h. So what can I say about h? Well, I could say that it depends upon something about this beta here. So I know they've got a beta and I've got a h here. So I'm not going to work that out, but I can say that the h depends upon the size of C. If you think about it, if I made my similar triangle but smaller, so if I made it like this, scaled it down, So we've got a beta there and an alpha there. Now this length, which we'll call L1, and this length here, L2, when we scale C down to L2, the height will be scaled down by the same amount. So for this triangle, which is the big one, the area of the big one, is going to be the base times the height, which is dependent upon C by some proportion. So I'll call that portion, I don't know, constant K. So it becomes KC squared. Is that making sense? So the H is always going to scale it's going to scale by the C base. Now, what happens if I look at these other triangles? Well, look at this one here. Let's whiz it around. So we've got this one here, so that's going to have the beta this side and the alpha that side. So that's my length A. So move around and that's your length A. So that's going to have a height, and so the area for your A triangle is going to be the base times by, it's a similar triangle, same one as before. We've got the beta on the left, so this height must also be dependent upon A by the same constant. So that we'll put that in, K times A, so that will be KA squared. What about this triangle here? Well, we've got a base there. Let's flip that around. So this one I've rotated. Yeah, rotated around like that. And I feel I've made a mistake. Looks fine there. So here we've got, I'm going to take this triangle here, rotate it anti-clockwise, beta and alpha there. So its base is B. So when we come to look for its height, we can say that the area of triangle B is going to be the base, which is B, times by the same constant factor that you need to scale to get to the height, and that would be KB, and so that gives you well, KB, that will give you KB squared. Now you can see where Pythagoras' theorem is coming from. So you say to yourself, right, so the area of the big triangle is going to be KC squared. The area of this triangle, I see there, yeah, that's why I would make. Sometimes I take that triangle there and take that down, but I've flipped it in space, so therefore it's not a problem. So if you went back and you had look at, well, say what's the area of that triangle, you can also say, well, the area of a triangle which has got beta on the right and alpha on the left is the same as the area of a triangle with beta on the left and alpha on the right. So you can use similar triangles, you can use rotating triangles, and you can use flipping the triangles. So here the area of our A triangle, that's that one there, is going to be KA squared, and the area of our B triangle is going to be that one there, KB squared. So divide through by K and we get Pythagoras. Geometry, bit of argumentation there. Not beautiful. He was only 11. Come on, give the guy a break. Stop.